Okay, so I had a question about the pre-lab for the rigid body motion experiment where you're asked to show that V equals half R omega. And so how do we do this? Well, let's look at the situation. We have a disc, center of mass of disc at the center, the radius of the disc is R, and we have a force F acting on the side of the disc like that. And we need to decide how is this disc going to move. Now, there's a neat trick you do to this, which is you say, to this rigid body I can add any forces I like, provided they have no net force and no net torque. Wouldn't be true for not a rigid body, but for a rigid body that's what you do. So let's add them. I'm going to add the following three forces. A force the same as the original force, and then two forces, each a half of that, going the other way. Sum total of these forces 0, F down, F up. Torque, take the torque about this point, no torque from that, and the torque from that, and the torque from that cancel each other out. So no net force, no net torque. Let's put my original force back in. There it is. So now let's add the new forces and the original force, and we get a force through the center of mass, and these two add up to give us a half F in that direction, and this one remains on its own there to be a half F. And so now you can see that we have one force acting through the center of mass, which will cause linear acceleration, and two forces acting through the edge, which will cause no linear acceleration but will cause angular acceleration. So the linear motion, we just have the force is equal to F. The angular motion, we have torque is equal to a half F, the force, times R, the radius, and there's two of those, times two of those, which is just equal to Fr. Okay, so now we've got the linear force and the torque. So the linear acceleration A is equal to the linear force divided by m. The angular acceleration alpha is equal to the torque over the moment of inertia, which is equal to Fr over 1/2 mr squared, the moment of inertia of a disk, which is 2 over r times F over m. Okay, so now we are asked to find the velocities, angular and linear. So therefore the velocity is equal to the integral from 0 to t of F over m dt, and the angular velocity is the integral from 0 to t of 2 over r F over m dt. Alright, now looking at these, in our experiment, F, the force, should be constant, okay, but maybe it's not. Maybe it varies because you see that tape being blown by the air wiggling. Maybe it's slightly varying the force, but it doesn't matter if it's constant or varying, because in each of these you can see we'll write this one as v equals 1 over m. Well, actually, no, we'll just write it as integral 0 to t of f over m dt. And this one we'll write as 2 over r, the integral from 0 to t of f over m dt. And what you can see just by looking is that that is a common term. So omega is just 2 over r times v. Or v is r over 2 times omega. So that's what we get. It's very straightforward, and it doesn't rely on the force being constant. It does rely on one thing. It relies on v naught equals omega naught equals naught. In other words, they start from rest, because when you do these integrations, in each case there's an arbitrary constant of integration, and if that arbitrary constant of integration is different from here to here, then this relationship won't be true. So to make it the same, we can say that, or we could say simply that v naught is 2 over as r over 2 omega naught. As long as that one's satisfied, it's the same deal. You'll still get that working. Okay, so that's pretty good. What makes this experiment neat is the thing you're asked to plot is theta versus r. So again, you just need to integrate the velocity and integrate omega to get the angular displacement and the linear displacement. And this is fine, and you should do this. And when you do it, you get r equals the integral from 0 to t of f over m dt, and it's the integral from 0 to t of all of that dt. But basically, again, everything on the right is exactly the same, and so you're going to get theta equals 2 over r times r, like so. So if we draw a graph of theta versus r, we should get a line. It doesn't have to go through 0, okay, but it should be a nice line, and the slope of that line, slope equals 2 over r, okay. And what's beautiful about this is it doesn't rely on our force being constant throughout. That force can be changing throughout, and this relationship should still be true. So you get nice results here regardless. There's another reason why theta versus r is plotted, and that's because this experiment dates back to the 60s, the 1960s. It's a very old experiment, okay? And when you measured in those days, you measured directly r and theta. You had a little measuring sheet that you actually held over an actual photo, and you made measurements. To calculate the velocity, you had to take a couple of r values, r1 over t, 2 r values divided by the time, and to calculate omega, you had to take 2 theta values and divide by the time. To calculate the acceleration, you had to take 2 velocity values and divide by the time between them, and to calculate the angular acceleration, you did the same. Now, you're going to find this hard to believe, but in 1970 there was no such thing as a pocket calculator, or any calculator really, certainly not available to university students. So to actually calculate a table of velocity versus time and angular velocity versus time meant doing subtractions and divisions and in such a way that you got another table, and this was a pain in the neck. Much easier to do a graph of theta versus r and then just get the slope.